Hello and welcome to the makeup lab for Spandex Gravity. Today we're going to be talking about how gravity works. To do that, we're going to be using a model. A model is just a representation that we can visualize much more easily than we can the real system, or that we can control more easily than the real system. So this is a piece of spandex that is stretched across a frame. Notice that when I push down, it's a very stretchy material. And this is a two-dimensional surface. 2 dimensions means I can go backwards and forwards, and I can go side to side on this surface. There's no up and down to the surface as far as the material itself. And so this is 2 dimensions. Our world is 3 dimensions. What we typically walk in and exist in is a 3-dimensional world where we have up and down, left and right, and forward and backwards. And those are our 3 dimensions. There's a 4th dimension, and the 4th dimension is time. And we're always moving forward in time. We can't move backwards in time, but we do move forward in time, and so we call that the 4th dimension. And masses in our 3-dimensional world bend space in the direction of time, and this causes gravity. So to understand that, we're going to be representing our world or our universe as this 2-dimensional sheet that can be warped by mass. So that's our goal today, is to just use this surface to represent the warping of space by mass. So we're going to go ahead and get started. You need to push pause between the numbers so that you can write down your answers or make predictions at the appropriate time. But I'm going to keep going through this pretty quickly. Just push pause when you need to. So on number 1, what does the spandex represent? Like I said, it represents space and time in our universe. Number 2, describe the path of a marble that is rolled across the spandex. So I'm going to take a piece of a piece of marble, and roll it across the surface of our flat universe here. So here we go. So ignore it when it hits the edge, because that, of course, is a little bit different. But as it's traveling across the spandex, you need to describe the path. I'll roll one more so you can see it again. Number 3, what happens to the spandex when a small mass is placed at its center? So for the small mass, I'm going to take a golf ball. This is sponge ball. And I'm going to put it right in the middle and watch what happens. Now it's a little hard to see in the video, but it's deforming the spandex just slightly. So write down what you see. Now I'm going to take that off for number 4, and it says what will happen to the spandex when a large mass is put on the spandex. So I'm going to go ahead and take a large mass, and the large mass I'm going to use is 2 weights for a baseball bat. I'm going to go ahead and put those right in the middle, and you'll notice a difference from the small mass. So write down your observations of what happens. For the next few demos, the large mass is going to stay in the center of the spandex. So if the spandex represents space-time in our solar system, so this is our solar system, the space and time in our solar system, what do you think that large mass in the center represents? What's in the center of our solar system? Number 6, if a marble is placed on the edge of the spandex and we release it, what will happen? So I'm going to have the marble here, and I'm going to release it. Make a prediction of what you think the marble will do. Again, push pause if you need some time. So on number 7, it tells me to go ahead and carry out number 6. So I'm actually going to let it go, and we'll see what happens. So watch. I'll go ahead and do it again so you can see it one more time. So did it actually behave how you predicted? Now go ahead and answer the questions in number 8. So now that we have finished number 8, let's do number 9. How would the acceleration of the marble change if I put a small mass in the middle instead of the large mass in the middle? So I'm going to take these marbles off and the large mass off, and I'm going to put a small mass, the golf ball, back in the middle. And now you're going to predict what will happen if I let the marble go towards the smaller mass. So write down your prediction. Push pause if you need to. So I'll go ahead and do it. I'm going to release the marble towards the smaller mass. Oops. So it went past the mass in the middle. I didn't want it to go past. I really just wanted it to hit the middle. So let's try it one more time. Let's see if we can get it to hit. Nope. So all we care about is the motion from here to the middle. Ignore the motion once it passed. That's not what we want to actually observe. So the motion as it's going down towards the marble and then stops right there. So does gravity seem to be affected by mass? Did changing this mass affect gravity? So now, how do you think we could test if gravity is affected by distance? Go ahead and write down an idea of how you think we could test if gravity is affected by distance. Okay, I'm going to show you one way you could do it. It may be different than the way you wrote down, but let's go ahead and see. I'm going to put a large mass right here in the middle, and I am going to take a marble and I'm going to roll it towards that large mass. Here is a marble, and I'm just going to roll it. Notice that I'm going to keep it pretty close, and so when they're close together, watch the acceleration of the marble towards the mass. Okay? Again, notice the acceleration. Okay? Now I'm going to move the mass much farther away. And I'm going to do the same thing. I'm going to take the marble, now it's a lot farther away, and I want you to watch the acceleration of the marble from a distance. Again, ignore once it passes the mass, ignore that. We're just looking at the motion as it travels towards the mass. Let's do it one more time. Okay. What did you observe? And again, we're looking at the acceleration towards the mass. We're not looking at any motion past the mass. So on number 14, does distance affect the gravity between two objects? And support your answer with observations from number 13. So we're going to put the sun back in the middle. And this time, we're going to see what happens if we give the marble a little sideways motion. Instead of just going straight down towards the center, what if we give a marble a little bit of sideways motion? So on number 15, we're just going to give it a little sideways velocity. So go ahead and watch and write down your observations. So just a little bit of sideways motion. And you'll notice that there's a lot of movement there. So describe that motion on number 14. Sorry, number 15. Now we're going to go to number 16. Again, push pause if you need to. On number 16, we're going to give a little more sideways velocity, a little harder. So watch what happens when I give it a little harder push sideways. Notice there's a difference in behavior. So write down your observations. For number 17, it says what happens if the marble's given even more sideways velocity. So this time I'm going to give it a much harder sideways velocity, and let's see what happens. So write down your observations for that. We'll do it one more time when I give it more sideways velocity. So on number 18, which scenario represents a planet in orbit around the sun? 15, 16, or 17? On number 19, it says that our marbles eventually crash into the center of mass. All of them eventually, except for the one that escaped off of the surface, all of them eventually crashed into the center. Planets, of course, do not crash into the sun. What is present in our Spandex solar system between the marbles and the surface? What is causing the marbles to slow down so that they eventually hit the center? Something that's not present in the solar system. Something that doesn't slow down the planets, but does slow down these marbles here. This is one of the problems with this scenario, with this model, is that the spandex does have this force that's slowing the marbles down. Whereas in real life, there's nothing to slow the marbles down, nothing to slow the planets down. Our next question says, do marbles traveling far away from the center of mass have faster or slower orbits than marbles traveling close to the center of mass? So we're going to do one marble that's close to the center, and we're going to put one marble that's far away from the center, and we're going to roll them and just see what happens. So does the far away marble travel faster or slower? So here we go. And then number 21 says, do marbles traveling far away from the center mass have longer or shorter orbits than marbles traveling close to the center mass? So from that last demo, you can write that one down too. Number 22, is a planet's orbit most similar to the radius, diameter, circumference, or area of a circle? So when I have this marble going around, that's like a planet does that path, is that best represented as the radius, diameter, circumference, or area of a circle? So now I'm going to trade out the center mass, which is heavy. I'm going to trade it out for a lighter center mass. And question number 23 says, if the center mass was traded out for a lighter mass, and I'm just going to put the pool ball in the middle, which is lighter, predict how you think this will affect the orbit of the marble. So now I'm going to go ahead and put a marble on here, and we'll see how that smaller mass affects the orbit of the marble. You'll notice there's definitely an effect. Go ahead and write down your observations on 24. For number 25, we're going to put the heavy mass back in the middle.